Let's do checkpoint 6.21. They want us to calculate the flux of this vector field x plus y comma 2y across the line segment from 0, 0 to 2, 3, where the curve is oriented from left to right. So if we graph this 0, 0 to 2, 3, the line segment that we're talking about is just going to be the line connecting these two, but the orientation will be from left to right. All right, we can parameterize this. I think we'll call it R of t. And remember the parameterization, it's going to start with the initial point for a line segment. It starts with the initial point, and then it'll be the difference of the 2 points with the ending point first, the head, minus the tail. So this will end up being 2t, 3t, and our limits of integration, or our limits for this parameterization, will be from 0 to 1. All right, now that we have that information, let's figure out how to do the flux. And the flux has this formula where it's going to be the vector field dotted with the normal vector, the unit normal vector, ds. Now, that is probably not an easy working definition to deal with. And so what we want to do is we want to rewrite or try to revise a few things. The normal vector in 2 dimensions can be obtained by given our parameterization with x and y, it can be written as y of t comma negative x of t. Now it has to be a unit vector, so we're going to divide by its magnitude. I'm sorry, this is prime, x prime of t comma, or y prime of t comma negative x prime of t, and divide by its magnitude. You're going to square them, so I'm just going to rewrite the order a little bit. And you can see that this is simply the magnitude of r prime of t. Speaking of the magnitude of r prime of t, we also know that ds is equal to the magnitude of r prime of t, which is essentially this whole denominator. And so when we do this dot product, well, when we do this product over here, the n with the ds, you can kind of cancel the magnitudes of r prime of t and have this left. And so we sometimes call this little n. And that is sometimes defined as the y prime comma negative x prime vector. Then we get to write our working definition. Our working definition for this flux integral, and that should be the integral from a to b, whatever our limits are. We know what our limits are. The function evaluated at r of t, and we're going to dot with little n, and then dt. All right. All right, so that means we should probably figure out what f of r of t is. F of r of t. F is x plus y, and x is 2t, and y is 3t. So that's the first component. And then we have 2 times y, 2 times 3t. And we get our f of t. Now little n, we need to take the derivative of this parameterization, which is going to be r prime of t, and that is 2, 3 constants, so that's nice. And according to our formula, little n is going to be the y prime, so that's going to be the 3, comma, and then the negative of the x, which is -2. Okay, we will dot that and put it into our integral as we integrate from 0 to 1. And this, let's go ahead and simplify this to 5t, comma 6t. Dot that with 3, comma -2, and we should have a scalar function that we can integrate. We have 15t minus 12t dt, and that is 3t. We have integral from 0 to 1 of 3t dt, which is going to be 3/2 t squared from 0 to 1, and that's just going to be 3/2 times 1. Okay, so it looks like that's going to be the flux of the vector field along this line. All right, if we can draw the vector field, I don't know exactly how the vector field looks like. Let's say the vector field kind of looks like that. Not really sure, just guessing. But the flux integral tells us that we're comparing this, instead of like circulation, we're comparing this to some normal vectors. Actually, the normal vector should be going the opposite way, because it looks like the normal vector is defined to be +3 and -2. So what we're doing is we're comparing the vector field, each point on that line with the vector field, and comparing it with the normal vector. And not by comparing, I mean doing the dot product and getting your results and adding them all up. Okay, I hope that helps with finding the flux in our two-dimensional version. Good luck.